Welcome to today's week 7 live session for Advanced Research Trends in Software Technology. This will be the agenda, same as what we have been following. We will discuss a brief overview of week 7 and then we'll discuss some questions. These are the deadlines for the upcoming assignments. Assignment 7 is to submit by tomorrow and assignment 8 by next week. Please submit them on time. And for those who want to access the recordings are available on this link, and it's also available on the portal. You can find there is a problem solving session and where you can find all the links for the PPTs as well as the recordings. Let us start with the overview of week 7. In week 7, the main topic was first initially it was a continuation of the AC microgrid control and then DC microgrid and then hybrid AC-DC microgrid. We started with the hierarchical control, then control in DC microgrid, and then control in AC-DC hybrid microgrid, and different power management strategies for hybrid AC-DC microgrids. Let us start with the hierarchical control. This is the
Sir, good evening, sir.
yes, good evening.
Hello, sir.
Yes.
Sir, shall we discuss sixth week assignment, sir?
Okay, which question?
Sir, actually, that adaptive control systems relay coordination. Actually, the formula for calculating time setting is based on the two currents, I1 and I2, for primary protection and for backup protection. For primary protection, they are using the current notation as I1, and for backup protection, they are using the current notation as I2. In the previous week, they told that I1 is nothing but positive sequence component current, and I2 represents negative sequence component current. But in assignment 6, one of the questions they asked that for adaptive control system, based on which current. The options are positive sequence current, negative sequence current, and two more options are there. Based on the formula for calculating time setting multiplier, it's based on two currents, positive sequence current and negative sequence current. Actually, in the last week too, I tried to discuss the same question. Based on the formula, two currents are considered to calculate the time settings, but the option is not available only for the option is only positive sequence or negative sequence or some other. And the answer they told that it is negative sequence component current. Why not positive sequence current for calculating relay coordination under the category of adaptive control systems?
They mean by relay coordination mean for backup protection. For backup protection, the negative sequence current has been used. That is why they have marked the answer as negative sequence.
So for adaptive control system, primary protection is not going to be considered.
No, it is considered, but actually the question is for relay coordination. For relay coordination, it will be the backup protection will come into picture. For backup protection, negative sequence has been used. That is why the answer is negative sequence.
Okay.
It's because of that relay coordination.
I thought that for adaptive control system, it's considered both for positive sequence and negative sequence. That's why even the last week discussion class 2, I tried to ask that question, but you are not permitting me to discuss the current week assignments.
Actually, yes, we have been.
Because of that, I lose the marks, sir.
No problem.
because the name itself, the title itself, they told the PSQ components. PSQ stands for positive sequence. No, that's why I choose positive sequence current. Even the flowchart also, the title of the flowchart, they told that PSQ. PSQ, everywhere they mentioned PSQ. So I thought that it is positive sequence component current.
Actually, a little bit, its question is little different, we can say. It was because of main term in the question which changed the answer is relay coordination. So
Okay, sir.
overall the
Sir,
prediction still
your voice is so
is
low, sir.
now, is it better?
Yeah, now it's
Yes,
okay,
sorry,
sir.
the mic was
Okay.
within the headphones.
Okay,
Actually,
sir. Thank you,
we
sir.
have been asked to not discuss the current week assignment questions. That is why I didn't discuss that last time.
Okay, sir. Thank you.
So, shall we continue?
Yeah, please, sir.
Yeah. So we were discussing about this hierarchical control. So week 7 starts with this hierarchical control. So where this P and O, this is distribution network operator. So the DNO is responsible for maintaining this management, to manage the operation of these low or medium voltage distribution networks where more than one microgrid exists. So here in this we can see n microgrids are there, 1 to n. These are the different microgrids, and this is the distribution network operator wants to control all these. So that's why we have a global control here, which is a centralized control. And then each microgrid is having a hierarchy of control. So overall, this is also one hierarchy. So the topmost is global control, and then next level is each microgrid, and within each microgrid we have these three levels: local control, secondary control, and the central and emergency control. So each microgrid will be having these three controls. The local level will be specific, BG specific for each generator, for each distributed generator. This will be local control, so it will be managing its own voltage. And then comes secondary and central and emergency control. Same thing. So global control is always a centralized control. And then this local control, it is always decentralized. It is specific to that generator. Generally, the conventional method is the loop control that we also have for these conventional generator alternators. When we study this parallel operation of alternators, we have this loop control where frequency versus speed. So different generators have different characteristics, and they want to meet certain load. Depending upon the load requirement, they will share power. Depending upon their together, suppose there are two generators, they have to combine together. They have to meet a demand or supply a demand. Then how they will share that PD, or you can say increased demand, delta PD. How they will share among themselves. That is decided by this group characteristics. Where finally they have to maintain common frequency. They have to do it in such a way that frequency remains same and load is also supplied.
But if it is a DC, but if it is a DC, what you say, microgrid, then the frequency control is not used.
Yes, it is for AC grid. This is not for DC. The DC frequency is there is no frequency. Then we have to go for this VP. True. Then power will depend. Voltage will depend upon power. In that case.
So in that also, whether it is a droop also, that in microgrid of DC, in that also there is a always declined droop slope.
Yes, droop is always like this.
For AC it is there a
Yes,
negative slope.
for
But
DC also.
what I want to ask, why for the DC it is a negative slope?
So you're saying it should be positive?
No, it cannot be defined. I think it may be positive, it may be negative, but strictly negative should not be there. What I want to say.
Because suppose if it is positive, let us consider that it is positive. So it means the more the power is being drawn from a generator or from any distributed resource, the voltage across its terminal is increasing. But this will not happen.
Like say suppose daytime the PV voltage increases. So now if there is a load increase in the daytime, so then voltage is increasing of PV, na? Distributed, say suppose if we say it is a microgrid of solar microgrid. So then its voltage will increase when the temperature will increase afternoon.
Yes.
So at that time, if suppose power requirement is there, so it may be flat then. At that moment, the slope may not increase, but it may be very okay. What you say, very less increasing slope.
So actually, droop is, unless it's adaptive, droop is fixed for the inverter. Okay, and second thing is this droop will come into picture when the generator has to supply a load. If no load is connected, then even if voltage is high, this droop characteristics has no meaning. So it comes into picture when a source is there and a load is drawing power or current. So it will draw power in the form of current. If it is drawing a current, then what will happen? Then what happens? That is defined by the load characteristics. So suppose here this voltage source is there. And it is a load is drawing current. So if we consider positive slope, then on this axis it is power. So if current increases, that means power drawn is being also, that is also increasing. So if I am increasing current, that means I am increasing power. So according to this curve, what will happen? Voltage should increase. But will this happen for any kind of voltage source? For any kind of source, if we are drawing current, will the voltage increase at its terminal? Will this happen?
Voltage will sir actually decrease when you draw current
Yes.
for any load.
Yes, because this is the, even if we consider some impedance is always there, and this is the internal voltage of that voltage source, then V minus IR, some drop is always there, and more the current is drawn, more this voltage across the terminal will reduce. So that is why this curve is also like this. Similarly, for a generator, when we say frequency versus power, if the load increases, the
Oh, that
electrical
is clear, sir. That is clear for that. For generator, I just want to ask a question.
yes,
That side is clear. Frequency versus power, that is clear. But what I want to say, is there any situation wherein the PV cell or can we say generally it is a droop control only? Can we say like this? Whether irrespective of DGs.
yes, DG is droop control is always negative slope only. Because voltage is reducing. With the more we drop, more the load increases, voltage will reduce. That will happen irrespective of any kind of generator.
Okay, okay, sir.
Because what you are saying that is correct. Voltage will increase if irradiance increases for solar PV. But for that increased voltage also, if we connect a load, that voltage will reduce. These Joule characteristics come into picture when we are applying some load to the generator. So it tells us how the increase in load will be distributed among the parallel connected generators. So how the power or load will be shared, current sharing, power sharing, all this. So that is determined by this control. So it is where this local control is there. So it will determine how much that generator has to generate.
Okay, sir. Okay, sir.
So and then the secondary control is there. It can be it is distributed. Can also be central. Centralized schema is also there. These are the distributed schemes which can be used. Then centralized at central level, it can be centralized or it can also be distributed. So both type of schemes are possible for secondary and central level. Global, it is always centralized. So there are three kinds of control schemes. So what are one is centralized, and then you can start with decentralized. The last is so what is the benefit of decentralized one? The decentralized is very simple that we have been using it specific to each generator or each component, and it is quite robust and reliable because things are not connected. There is no communication. In centralized, the problem is there is one central control, and all others are connected through a single link. There is only one link connecting that generator to that central control. That is through a communication channel. And if this communication link or channel fails, then this generator will not receive any power. And it will not know how much to get. It will not know. So here reliability is a concern. So that is and all the problem with decentralized is that it is difficult to meet a common goal because these generators, this generator is not, they are not communicating with each other. Only this central, sorry, in decentralized, they are not communicating with each other, and also each generator is doing its own work. They are not concerned about meeting a common goal. So that is difficult here. In centralized, we can achieve a overall system goal. But here problem is alive. If communication link fails, then we will not be able to achieve that goal. That's why to overcome the problem of these two, distributed has been developed. Distributed schemes have been developed. So here we have central also. So we here suppose these are the different entities, so they can talk to each other. So they can talk with each other, with neighbors, and in that way, even if one link fails, they are still able to achieve their goals because they are connected in a mesh kind of mesh. They are connected with each other. So this is the figure so this is centralized. So here we have only central controller, and which is connected to each local controller through a communication. But if this fails, then
Excuse me, sir.
yes.
So someone is taking the class along with you, sir.
Actually, we can learn just a minute. Yes.
Thank you, sir.
Sorry for the distance. So this is the centralized, right? And then we discuss this decentralized. So there is no communication at all. Then is it fine? Okay. So thanks for reminding. This is decentralized. Here each one is taking care of its own generator. No communication at all. Here there is a communication with neighbor also. So if suppose this link fails, then still because this is connected to this, it is still able to do it. So that is the advantage of distributed, but problem is it requires more communication infrastructure. So communication cost increases. Here if we also think in terms of computation, then what happens in centralized control, this central controller will be taking all the decisions. So it will be taking inputs from all these controllers, and then it will also give some decisions. So in terms of computation, this central controller will be doing a lot of work. It has to solve a bigger problem, big optimization problem. It, so computation requirements are quite high in case of central controller. But in case of decentralized, it's very less because only we are concerned about only one solving one optimization for a smaller. A single generator is doing its own optimization. So that is also one advantage for this decentralized or distributed over centralized. So these are the hierarchical controls that we discussed. There are four layers. One is the global control. Let us start with the local control. So this is from top to bottom.
So a lot of background noise is there.
So Seven. So it is from top to bottom. You can see this is at the bottom local control for each DG. So each DG will be maintaining its stability by measuring and controlling the local sectors. And then it controls so that it can operate in a normal operation. And it is always decentralized. One level higher is this secondary control, which enables the power sharing for parallel configuration of DGs. So here you can say this can be done using truth control also. And it also compensates for voltage and frequency deviation caused by load variation and local control operation. So if suppose this is trying to achieve something and it is not able to do that properly, then this secondary control will take over. It will do the rest of. You can say this is a coarse control and this will do a fine tuning. And much this is more final. So it improves the power quality and system performance, and this can be centralized or distributed. These two schemes, these two central and secondary control can be centralized or distributed. This is always decentralized and this is always centralized. This global control. And central control is specially, or it is also called as the emergency control. So it's particularly important in islanded operation because it monitors the secondary. It always monitors the secondary and local control, and for islanding, it also detects. It keeps track of the status of the microgrid, whether it has get connected to island or it's an island. So island detection, connection and disconnection to and from main grid. That is an important task of this center. So this islanding detection, disconnection to and from main grid, from the main grid, and emergency control and overall protection scheme all are a part of this center scheme. You can say this is microgrid central control (MGCC), which we have seen in the previous classes also. So it will have inputs from all the generators, all the DGs, and it will monitor everything. It will monitor how the secondary control is working, local control is working, and coordinate with all the generators. And this MGCC will also coordinate with the other microgrids through this global control. This global control manages power flow between given microgrid, other microgrids, and the main grid, and it is outside the microgrid, as we have seen in the previous unit also. It will receive power reference from the demand management system, and it is centralized. So these are the different DC microgrid control. DC microgrid control also there are three types of strategies. One is decentralized, then centralized, and then distributed control. So there are different types of strategies for decentralized control. Voltage leveling, DCI signaling, power line signaling, and similarly for distributed control also. Then DC microgrid control. Just as we saw in AC microgrid also, AC microgrid there can be different three modes. One is grid connected, then islanded, and then there are transition. So one is from grid connected to islanded, islanded to grid connected. These two modes are. So this is a restoration. So here we have grid connected and islanded signal in the DC microgrid also. In an islanded also there are two types of cases. One is only single microgrid is islanded. Another is a group of microgrids have been islanded and they are connected to each other via these tie lines. So single microgrid in this decentralized strategy is more reliable and cost effective. In this case, what will happen? DG operates in MPPT or off MPPT based upon the storage level. What is the charge, state of charge of the storage? That will decide whether the PV orbit will operate in MPPT or off MPPT mode. And then storage or renewable will regulate the DC voltage. In multi-microgrid also, what will in this they are connected through this tie line. They will form a cluster. So advantage, what will happen? Advantage for this single microgrid over DC microgrid is that suppose in single microgrid, if this is one microgrid, if load is very less and energy storage is not fully charged, and RES is generating more, then what can be done? The excess generation can be used to charge the battery. Correct? So in that case, we would like to get maximum output out of the renewable generator. So we would like to operate them in MPPT mode. But suppose if energy storage is already fully charged, so that excess generation cannot be used to charge the battery. Then it has to be cut in. So we have to shift from MPPT to off MPPT. That is why this depends upon the state of charge of the battery. Whether storage is discharged or charged, it will determine the operation of the renewables. This is for a single microgrid. But what happens? Suppose if we have a cluster of microgrid and one microgrid is excess in generation, another microgrid is in deficit of generation. So now in this case storage was fully charged. So the renewable has to operate in off MPPT mode. But if there is some other microgrid which is connected to it which is deficit in power, then the renewables can still operate in maximum power mode. And then supply the excess generation can go to the F is set by to either for supplying load or for charging the storage. So, what do you know the principle for maximum power point tracking? Anyone of you? What is the principle for maximum power point? It's based on a theorem. Maximum power transfer. Have you heard of this? Anyone of you know this?
ये जो पीछे जो आई थिंक तो पीछे ना कुछ आवाज ज्यादा हो रही है, उनको थोड़ा बोल दीजिए आप प्लीज. हेलो.
Next time, change the place. So, do you know this maximum power transfer?
Sir, MPTT is maximum power point tracking.
Yes.
That the solar rotates itself according to the sun or according to the light source from where it is getting to get the maximum power. But sir, MPPT and MPTT both are same.
Oh, I was thinking this maximum power point tracking works on this principle. Principle is this. This is the principle which is used.
MPPT is an algorithm and which is based on maximum power transfer theorem.
Yes, correct.
Yes,
You know
sir.
about this maximum power transfer?
So, but this MPPT is only for the PV cell, not for
No,
others.
no. It is for wind also. For wind also we have this.
No. See, I think then it is for the all DGs or only for the wind and PV cell.
Can be done for any source.
Sir,
There
it
are
is not
some.
only for solar.
No, it is not only for solar.
Okay. Sir, maximum power transfer theorem is that when source impedance will be equal to load impedance.
Yes, correct.
When
This is ZS and this is ZL. So that is RS, RL. If RS is equals to RL, maximum power can be transferred. These two resistance has to be equal. So how is this done for solar? This is done using this converter. So if we have solar, our load is fixed. I want to draw something. My requirement is something I cannot change load. My requirement is fixed. But this is a boost converter or a buck boost converter, DC converter, and this is a solar PV. So now I want to make this load resistance, which is my requirement, and this source resistance. Both I want to make equal, so that maximum power can be drawn from the solar PV panel. So how to do that? That is done by this converter. So converter tries to make this impedance Rin equals to this load resistance. So it switches in such a pattern that this happens. So that is the switching algorithm which is used. So boost converter has to operate in such a way that these two resistances become equal. If that happens, maximum power can be drawn for a particular irradiance level. And if the irradiance level changes, then that point will again shift. For that irradiance level, we have to draw maximum power. Similarly, it happens for the wind also. For a particular wind speed, we have to draw because we have seen that this is the PV characteristics for a particular temperature and irradiance. So this is the characteristics, and we can operate on any point. To draw maximum power, we have to operate on this point. So this converter will ensure that the panel, the PV panel operates only at this point, so that we can extract maximum power. So it's the work of that converter to maintain this point. If the irradiance changes, irradiance level, the curve shifts, then this point has to shift to here. So again the converter has to change its switching pattern to ensure this. Similarly with temperature also. If anything changes, the converter has to ensure this point of operation. Is this clear?
So
Sir,
that
what
why
will
it is
be
bus? So
Yes.
why it is boost? Always boost converter is there?
Buck boost can also be used, but buck is not used. Why buck is not used?
sir? What will be full form of MPPT?
MPPT. So it's MPPT is maximum power
Maximum
point
power point.
tracking. For this we have several algorithms. Simplest is perturb and observe. Then we have incremental conductance. Means P and O is the simplest. Then
Sir,
incremental conductance is another.
sound waves are breaking. Sir, for wind turbine, how we can detect that MPPT point?
For for wind also we
Same,
have such curves.
same thing.
For
Okay.
wind also we have these curves. For each beta, for each pitch angle. For different wind speed we have these curves. So pitch control has to be done in such a way that we operate on this point.
Okay, sir.
Yes. Any other question? So there's MPPT. Yes. Clear?
Sir, I have one question from previous slide, sir. Sir, what is the difference between means centralized and distributed? Basic difference.
Yes, we saw here.
Centralized control and distributed control.
This is just this is centralized control. Control. There is only one central controller.
Yes, sir.
There is a lot of background noise from your side. Can you mute yourself or something? Yes. So there is only one central controller, and each controller is linked to the local controller. There is only one link. So if that communication link fails, then there is no control. The local controller has no input. It doesn't know what to do if there is only centralized control. So it receives inputs, control signals from that central control. How much to produce, what should be the current, voltage, everything.
So for global control means it is central also, but it can't be distributed also.
Which one? Global.
Oh, global.
Yeah, global is always central. But it, yes, we can make it, but distributed, uh, it, generally we don't make it distributed because we already have a hierarchical control or another control. That can also be made distributed also, centralized in this global control also. But actually we want someone, a distribution network is operator is there. So we always want some kind of control. If something goes out, there should be a central control is there, it can always do something. So it can interrupt. So it's because of that we want to keep something. The system operator wants to keep an eye on everything. That is why it is centralized. But the secondary and central control they can be distributed because there are multiple DGs and they can communicate with each other to do perform that particular task. So we are here multi microgrids. So they together they form a cluster, and because of that they can interchange power between them. And as a result, there can be overall improvement in reliability because one microgrid can supply the requirement of the other microgrid and vice versa. And that is why there is improved reliability, better utilization, and suppressed aging and stress of components, and all these things can be achieved. It will also reduce the maintenance cost and expand the overall lifespan of the grid. Similarly, if these multi-microgrids together their inertia is sufficient, they can also provide stability to the main because they are now a cluster, a big microgrid formed using different microgrids. So that is possible. This comes a good advantage. Multi-microgrid has a good advantage. So is it clear how the, when the renewables will operate in MPPT and when in off MPPT? Is this clear?
So once it is not charged, then it is operate in RES.
Can you repeat?
Once ESS is not charged fully, then
Then
it is in RES mode.
RES is renewable can be in these two modes, in
When it is
MPPT
in MPPT,
or off MPPT mode. So if ES is not fully charged, is less than its let's say 90% of SOC, then RES will be in which mode? because it is not charged, and if load is also less, there is excess renewable generation. That excess renewable generation can still be used to further charge the storage. So in this case, we would like to operate the renewable generator at its maximum power so that we can extract the maximum power. But once it is fully charged, then we cannot charge it further. And if load is also less, excess generation is there, what can be done? So we shift to off amplitude. But if this microgrid is connected to some other microgrid, then no need to shift to this off MPPT mode. We can still be in MPPT mode and supply this excess renewable generation to some other microgrid. Is it fine? The loads are also defined as critical and non-critical. Because there is one microgrid which is solar dominated, and in the evening solar is not there, late evening solar is not there. Only storage is there, and we still have to meet the loads. We have categorized them into critical and non-critical. Now storage is having certain SOC level. So it starts supplying the load. But gradually, it's what happens, its SOC will reduce. And it will not be sufficient. It may not be sufficient to meet entire load, the entire load. Then what we will do? Which load should be curtailed? Critical or non-critical?
Non-critical.
Yes. So we start curtailing this non-critical. Anyhow, we have to meet this critical. These can be hospital. So we always want to meet them. So more as the SOC goes down and down further, these will be curtailed further, and we'll try to meet this critical. And then microgrid is connected to the main grid via a grid voltage source connected. So this can act. This is a DC line. So this can act both as a converter, or we can say some rectifier, and inverter. So when will this voltage switch converter will act as inverter, and when will it act as a rectifier? So you tell. So there can be power flow in both the directions. Let's say this is P1, P2. So for which
What is this GVSC?
this is grid voltage source converter. Now it's a converter. It allows bidirectional power flow. It can operate both as an inverter and as a rectifier. So for which power flow, P1 or P2, will it act as an inverter? P1 or P2?
P1 it is inverter.
Yes, correct. Because this is a DC microgrid. We want, because of, let's say there is excess generation, then it can feed power to the main grid. Let's say storage is fully charged and load is also less and renewable is at its excess power. Then it can still be in MPPT and provide power to the main grid. So this is P1 current, and for P2 it has to act as a rectifier. Now one another component in this microgrid is storage. We can have hybrid storage. We have seen in week 3 also. One is battery, the second one is ultra capacitor. So which one has high power density but low energy density? Which among these two?
Ultra capacitor has high power density but low capacity.
But low energy capacity. So it is used for meeting this high frequency switching transits. So frequent switching operations, frequent requirements, spikes can be met by this ultra capacitor. In normal operation, the storage can. The storage has so this is high energy density and low power density is compared to ultra capacitor. So together they can work to do this, meet these requirements. So especially in this transition requirement, ultra capacitor can help. Any kind of immediate spikes need to be met. Demand has to be met. That can be met by this ultra capacitor. So overall, this can help in improving the life of the battery, because we saw that life of this battery depends upon this depth of discharge rate, discharge rate. So if discharge rate is quite high, then its life will reduce. So to take maximum benefit out of battery, we have to ensure that its life is also maintained. So it can operate over its full life cycle. So for that, we are using a capacitor so that these high discharge rates, such operations can be met by this ultra capacitor. Is it clear? Yeah. So let's go ahead. So next
So what is SOC?
SOC,
SOC
so
in ESS?
it's state of charge. How much charge is there in the battery with
Okay.
respect to,
So sir, if low charge, then load will have to marked as critical.
yes, if SOC is less, we can supply, we cannot supply the full load. We have to curtail the
Yes, sir.
load. We will only supply the critical loads.
Yes, sir. Yes, sir.
So next question for you is why do we go for ACDC hybrid microwave? What's the need for this hybrid combination? Why not go for AC or DC? What will be the benefit of using AC? answer? Anyone of you? We have studied AC, DC also. Why AC DC?
Because sir,
Because practically the loads comprises of both AC and DC. When we are without AC load, we are not going to run anything. Even in domestic applications or commercial applications, motor plays a major role. So usage of AC also be there, and DC lighting system also be there. That's why we move for AC DC hybrid microgrid system.
Yes, that is correct.
because sir, from DC microgrid we can also give to grid, main grid, and if required we can take from main grid to DC. Means both type of converters will be required.
But that is happening in yes. So we are saying conversion stage increases. That is correct. So this is correct. Loads are both AC and DC. Similarly, even generation, the sources, they are also both AC and DC. So here we have wind, here we have solar, we have fuel cell, here we can have micro turbines, small hydropower also, even biomass. All these are AC. Yes, DC we have storage. Even some kind of storage is also fall into AC. So we have wide variety of load and generate sources and both AC and AC several. What happens if we are in AC grids? We have AC grid. Then what will happen in AC grid? We have AC loads and we have DC loads also. We have AC generation also and we have DC generation also. Now this AC grid is connected to the main grid. Then if we have a DC load and AC grid is there, that means so we have AC microgrid. The supply is main bus is AC bus. If you want to feed a DC, then you have to convert this AC into DC. And if we have a DC source, then you have to convert this DC into AC. So we have this AC to DC stage, then we have DC to AC stage. Similarly, if we have a DC microgrid, then we have DC source, solar. If you want to feed a AC load, then we have to convert it into DC to AC. And if AC source is there, we have to convert it into DC. So AC DC, these conversion stages are there. Suppose, but if we have only we have this DC grid, this is AC grid, and we have only DC sources here and AC sources here. Sorry, only DC loads and no conversion will. And similarly for AC also, AC loads, AC generators. So using hybrid grid, we can increase the efficiency. We can avoid these multiple AC-DC, AC-DC, AC conversion and DC-AC-DC conversions. These we can avoid with AC and DC grids. So this is a major reason for moving to this AC-DC hybrid. So this is that what we have discussed. This is the classification. So AC, DC. In AC, the main bus is AC exchange of power is through AC platform. And common stages are DC, AC, DC. Well, if there is a DC source, then you have to convert it to AC to AC. Then DC load, and again AC to DC. If it is DC, then AC source, you have to convert it into DC, and for supplying AC load, you have to convert it again into AC. In AC/DC, we can avoid these conversion stages. This three stage. Is it two stage? Here main bus are both AC and DC. We have two buses, AC bus as well as DC bus. And the platform here is AC/DC. All the three, the main purpose is to have power sharing to and from the main grid and to increase the reliability of the loads. Because if all the three grids, when three microgrids, when connected in the grid connected mode, then if there is deficit, they can take power from the main grid. And if there is excess generation, they can supply power to the grid. In all the three. That is the main purpose of connection to grid. In AC/DC hybrid microgrid, there are two types of structures. One is structure 1, which is shown here. Second is structure 2, shown here. The structure 2 is very simple. Here, let us see this structure 1 first. In structure 1, also we have these stages that we were talking about in this previous here. We were talking about these stages. So it is there in this structure 1. So here you have two types of buses. One is DC bus, one is AC bus. And on both the sides, there are both AC and DC loads. AC load is there, DC load is there, AC generation, DC generation. Here also AC generation, DC generation, DC loads are there. So what is happening here? So this is the AC bus and this is AC generation. So we are first converting AC to DC and again DC to AC. Storage is bidirectional. So these DC and AC buses are connected by this interlinking converters. So DC, AC, and these are bidirectional converters to have bidirectional power flow. And this entire microgrid is connected to this main grid here. So entire this can be island. Then they will have to operate on their own. They have to maintain this both the voltages at these buses and voltage and frequency at AC bus and voltage at DC bus. All these three has to be controlled simultaneously. So here AC/DC are interconnected by interlinking converters. The generator storage load are both on AC and DC side, and this is preferred when major sources are both on AC and DC side. We can say the present system. We have both, but in particular area there may be cases where the DC loads are much more. So there DC magnet can be used. And if the source is also DC and load is also DC, then such type of structure too can be preferred. So here interconnection is by same utility capacitors. Here AC sources and AC loads are only on AC side. You can see here. On this is the AC bus. So here we have wind, main grid is connected here. Diesel generator is there and AC loads are there. And then DC sources and loads are only on DC side. This is PV, which is DC, connected through a DC-DC buck boost or boost converter. Battery, which is also DC. Ultra capacitor also DC. And DC load. So all are DC on DC side. So this is very good. These stages can be avoided if they are connected using the city capacitor. So sorry, converter. So there can be one intellectual converter or even more than one. So here we have okay, is it fine? So here we can improve the efficiency as well as reduce the cost because number of converters are reduced. All these I think this is now let us move to the power management strategies in grid connected. So in grid connected mode, there are two types of strategies for this power management. One is dispatched power mode and another one is the undispatched power mode. So in dispatched power mode, we are receiving the power signal, how much to produce. That is decided. In undispatched, whatever is being produced, that is directly fed into the grid. So in dispatched power mode, the microgrid behaves like a controllable source or load to the main grid. The main grid can control this microgrid, and that dispatched power, which is shared among all the different power sources within the microgrid. This is grid support. So grid support is included within this reference microgrid power. In case of dispatch power, since we are dispatching, we are saying we have to produce only dispatch P and Q. It can provide. So in grid connected mode, the microgrid can provide grid support services. And how to support that? What should be the required generation P and Q for dispatch power mode? This requirement is inherent in the reference which is given to the microgrid, and this reference comes from the main grid in dispatch power mode. And in undispatched power mode, since it is generating whatever is available, so this grid support services depends upon each individual generator, how much it is excess it is producing. That will decide how much it can support the grid. So in dispatch power mode, there are two modes. One is current control mode and one is voltage control mode. So in current control mode, the current is controlled to track the reference power, and then voltage and frequency are determined by the grid. In voltage control mode, voltage is controlled to regulate power, just as the conventional synchronous generators. And then in undispatched power mode, as we have already discussed, all the generator power, whatever is being generated, is fed into the grid. So for this, they have to operate in MPPT. So try to extract maximum power from the renewables and feed it into the grid. That is where DGs work on MPPT, and this storage are typically charged. So why not discharged? required be charged and not discharged. Can you answer? Can you? Surplus power, yes. Surplus power is there. Then surplus power with renewable or with storage. If storage is suppose storage is fully charged, yeah. So if there is excess generation, then storage in charge. Why not discharge? Can storage discharge in grid connected mode?
What is it, this SC?
Storage. This is storage.
Sir, what is GS?
This is grid support. So grid support services are provided by controlling PV and Q delivered to the grid. So in both the cases, grid services can be provided. But here in dispatched power mode, the grid service, the grid support signal are included within this reference power signal. However, in this one, undispatched power mode, the grid support services are realized through individual generator or storage. Yes, I was asking that can we discharge the storage? So here generators, all the renewables are operating in NPTEL. And we have charged the storage sufficiently. Now, should we discharge that storage to provide grid support services? Yes, ideally we can discharge, but we should also keep into mind that when renewable is not there, we should be able to supply the load. If it is in grid connected mode, we can always supply the load. But if storage is already there, then the requirement from the grid will reduce. So when the storage is fully charged and when within the microgrid the renewable generation is less, we try to discharge the storage instead of taking off from the main grid. So we do have to take care of the islanded node also in case of emergency. For backup also, we need that the storage is charged. So storage should not be fully. Some level of minimum level of SOC should be maintained for storage, so that when the renewable output is less, and in case of emergency, storage can provide. It can still supply the. That is why here also it is written that storage can discharge also for providing grid support services. But we have to maintain the SOC level for the low generation periods. Okay, is it clear?
Sir, what
Yes.
is actually undispatched meaning? Means grid is not dispatching the power.
Yes, correct. So here grid is whatever is being generated, everything excess generation is directly fed into the grid. Grid it now is deciding how much to feed. But here the generate microgrid is receiving signal from here grid. How much should be supplied to the grid? That is why it is dispatched, predefined. So it is predetermined how much to be supplied to the grid. But here it is not the case. Whatever excess is there, directly feed it into the grid. Is it clear?
Yes, sir.
Okay. Next is this again power management strategy. How these the linking converters they operate. Their mode of operation in different modes. Grid connected mode and dispatched is interlinked. So this is a summary of the entire operation of these different converters. So you can refer to this slide for your exams, for your quiz. So dispatch mode, the interlinking converter operates in called DC bus voltage control. It ensures DC bus voltage control. And the generators and or storage DC side, they coordinate with DG and storage on DC side for power balance. DC bus voltage control is done by interlinking capacitor. So converter. And DGs and storage on DC bus are on DC link voltage control mode. Interlinking converter is power control mode. So these are two different strategies. Either we can do this or do this.
Sir, this part is not understood, sir. Can you explain it again?
Yes. So in dispatch power mode, so we have different types, three components. One is this, and we have to control these things. One is interlinking converter. Then we have DC, and then we have storage. And in hybrid AC/DC microgrid, we have to control voltage at DC bus, voltage at AC bus, and frequency at AC bus. We have to control all these three things. We have to regulate them. How to do that? So these three components they have to work in particular mode to achieve to ensure that these are regulated. So for that we are saying how in which mode they should work. So for dispatched power mode, which we have discussed here in the previous slide here. The interlinking capacitor. So again, the capacitor interlinking converter. It operates in voltage control mode. So that means it will regulate the DC bus voltage and and the power sharing or power balancing on both AC and DC side will be done by these renewable generators and the storage on both the sides, on AC side as well as DC side. So they will coordinate with each other to ensure that there is a power balance. And if power balance is there, then frequency will be regulated. Correct? Is that clear? Yeah. So second is this. If the interlinking capacitors, sorry, converter, I should write it next time when we get converter. The interlinking converter, it is, if it works in power supply, that means it is regulating the power. Then the distributed generator and storage on the DC bus, they will regulate the voltage on the DC bus. The DC, this is the DC bus, this is AC bus, and in between we have the converter. So the generator here and storage, they will together regulate this voltage, DC bus voltage. And this generator on AC side and storage on AC side, they are in dispatched power control. This is AC side, this is connected to the AC main grid. And since this is a dispatched power, so the AC side generator are in dispatched power. So they will generate as per the signal received from the main grid. And that is why this interlinking converter, it is controlling the power, how it power should flow. And the voltage, since it is controlling the power flow, the voltage regulation is done by these DC side sources and storage. Is this clear?
Yes.
Similarly, for undispatched, in undispatched, the interlinking converter, it contains the DC link voltage and injects all the power into the grid, because in this mode we have to inject everything, whatever is being generated. And DG's distributed generator on both AC and DC sides, they work on MPPT control, extract maximum power and feed it into the grid. And storage, typically in charging mode, and maybe discharge for only for smoothing the output. The storage will be charged so that it can switch off whenever there is requirement, when the renewable generation is low. So it will discharge only for smoothing the output, and for that the discharge requirement is not that much, it will be less. So overall it will be charged. And if it is fully charged, then also MPPT will continue. No need to go into off MPPT. Now this is for grid connected. What will happen now? The microgrid is standalone. So in that case, there are these two: DC bus voltage control and AC bus voltage control. So in both the cases, generator and storage on DC bus link voltage, they control either directly through group control or indirectly through power balance. Similarly for AC bus also. And the interlinking converter, it can operate in either of these: AC link voltage control, DC link voltage control, or power control. I think this will be more clear when in the upcoming weeks there will be demonstration how this is being actually implemented. and it will be moved. Right now it's fully it's vertical. So main thing you have to understand is this part that if these three are the main things that need to be rectified. So if this voltage control is being done by interlink converter, then the power sharing, power balancing has to be done by the storage and the distributed generator, and vice versa. If they control voltage, then power sharing is done by this interlink converter. Next is so that was for power management strategy for grid connected or standalone. Now this is for transient or for loading conditions. So in transient operating mode, so, or we can say it's transition modes. There are two possibilities. One is grid connected to standalone, second is standalone to grid connected. When there is grid connected to standalone, there are two strategies. One is control switching, or it's switching the control strategy itself. We have seen here in the previous slide for grid connected and standalone mode, different type of strategies are used. So depending upon whether it is in grid connected or standalone, a particular strategy is used. So now if there is a transition from grid connected to standalone, then as per this methodology, the strategy should change. And for that we need to determine whether there is islanding or not. And for that we need the islanding detection techniques, which we have seen in previous weeks. There are active, passive, hybrid, or communication-based islanding detection techniques. So in this case, we need to detect first. If there is islanding, then there will be switching. Control methodology will be switched. There will be change in the methodology. Another strat, another methodology, another way is to use same control for both grid connected and switched. In that case, we don't need this islanding detection techniques because control is same for both. Then second one is grid connected to, so it's standalone to grid connected. So it's a restoration. We again want to connect the microgrid to the main. So for that, we need to synchronize the connection. For that, voltage of the microgrid and voltage of the main grid, that should be nearly equal, almost same. That we have to ensure. So for that we need to synchronization is very important for that. And for that there are active or passive synchronization techniques. In passive synchronization it assumes that voltage is very close and frequency only differs slightly. But in this there is no guarantee of fast and controllable synchronization. Yes, but in active synchronization there are two possibilities. One is one or more DGs initiate and others may follow. Another is that all the DGs they participate in the synchronization. So yes, there is a change in control scheme or uniform control can also be used. As we have discussed. Same scheme can be used for both grid connected and standard. But main thing is voltage synchronization has to be done before reconnection. That is the most important. Just as in conventional generator also, before connecting it to the grid, you have to synchronize it. Otherwise, there can be faulty. Otherwise, the connection can even be unstable. So this voltage difference has to be very less, and even frequency. So both V and F has to be made almost equal before connecting it to the grid. So that is why this transition is also very important, and synchronization plays a very important role, very important for this. Is it clear? So here one or more DJ initiate and other follow. So here they operate in current control. And here in second one when all the generators participate, they operate in voltage control. So the important thing is communication is very important. And based upon loading conditions, certain loads create problems. So constant power loads they can cause instability and also negative impedance characteristics. Now let us now move to questions. May overview took a lot of time. This
Sir, in on this first board, if there will be always the condition that RES will work in MPPT mode and energy storing in fully charged condition, there is always condition.
yes, because it is connected to grid, so can feed power. So if you want to feed power, then it's better to operate it even to maximum, try to extract maximum power from the table and feed it directly into the grid.
Yes,
This is B is the answer. Voltage and active power.
So the question is key control variable in DC microgrid are
C is
yes.
voltage and current.
No. This is B is correct.
Voltage and active power.
Yes. We have to control voltage and active. So we saw this B and P two characteristics.
Yes, sir.
These are the main control variables here. This is correct. Second question is this. This also we have discussed. Which of the following hierarchical control is correct from top to bottom? This is from top to bottom. So which one is correct?
Control. A will be correct, sir.
You have to see from top to bottom. Oh, sorry, sir. Bottom to top.
Bottom to top.
Yes, correct. Sorry. Bottom to top. So bottom to top. A is not correct.
Option C, sir.
C, sir.
Yes, C is correct because local, then second, then emergency control, and then global control. So which one is centralized here? Which one is always decentralized out of these two?
Local is decentralized.
Local.
And which one is always centralized?
Global.
Yes. And these two can be both utilized and distributed. Okay. Expression is this. Which of the following is true in case of conventional group control in the DC microgrid?
C answer, sir.
We have to see. This is reference here,
Reference.
not voltage, not DC microgrid. Yes, B is correct. References only, it will always be, it has to be upstream. Because that is what we want to achieve. Because we want to maintain that DC bus voltage. So reference is fixed.
Yes, sir.
Here you have to see this word. And which of the following decentralized control this we have not discussed today? Is is there for different types of decentralized control? It's limited to small renewable energy systems. This is a theoretical question.
DC bus signaling, sir.
Sure. It's voltage level. Why is this so that it's an also yes. This is not discussed in that detail. All these techniques are just an overview of them have been given in the lectures. So you can know the
So
basic.
how it is related to the small and large?
Even that I am not sure about that. I will have to check. But it was mentioned, so I just directly I made a question. I have to check
What is this
what
DC bus signaling method?
in DC signaling. Actually, DC was signaling. In this, all the distributed generators they are scheduled. They are divided into groups. In voltage leveling, single DG is controlled. There are no such groups. So there is a these two similar. These voltage leveling and DC signaling are similar method. Only the main difference is that in voltage leveling, individual source is controlled. In DC signaling, a group of these generators are scheduled together. So this should
Sir, why not the answer C for this question, sir?
answer C. Actually, it is
Root,
specifically mentioned for voltage leveling. So root control we can do for any. It's large or small doesn't matter. Because you see, if we see the conventional generators, then it may be a very big generator also. Still, we have to control for them. So the size of the generator does not affect.
Okay, sir.
Can we take next question?
Yes, sir.
This is we have discussed this. In hybrid storage system, which are the following devices help to
Supercapacitor.
price switching channel? Correct. So it's capacitor or total capacitors. It's very high. Next is this modern electronic loads. When they are connected to isolated AC microgrid, having a PV as single source of energy, the following conversion losses are natural.
DC, AC, DC.
Why DC?
Because PV will generate DC, then we have to convert into AC.
Correct. And then again DC. PV is AC. Sorry, PV is DC. And loads are DC, electronic loads. Sorry. That is why
Electronics load are mainly DC only.
yes, that is why we have those adapters, mobile chargers, laptop chargers, all these SMPS. They are all they have these DC converters. So DC is suppose if instead of I think this next question. This is the next question. So when a motor load is connected to isolated DC microgrid having wind as single source of energy, which are the following losses take place? So here motor load is there.
Option A.
Option A. Okay.
A.
The motor load is it requires AC, then it is connected to a DC microgrid, and then source of energy is wind. Wind is also AC. PMC. So AC, DC, AC. Yes. Next question. This also we have discussed. The role of interlinking converters DG then is storage, respectively in case of grid connected undispatched power mode of operation of AC/DC hybrid microgrid is so which will operate in PPT mode. So it is AC/DC hybrid microgrid and it is connected to the grid connected and undispatched. So what will happen in undispatched power mode?
B, sir.
Teacher?
B.
B, B operates in MPPT
Electricity and that
always charged. Is it true? Any, so is B correct? Or it can discharge also. Yes, C is correct. We saw it can discharge to smoothen the.
D is answer then.
How deep?
This undispatched power is also to be considered.
Yes, yes. Undispatched is it's an undispatched power. So in undispatched power mode, we saw that whatever excess generation is there, we always want the reliever to operate in amplitude. We want to extract maximum power from renewable so that we can feed it into the correct. Yeah, so we will so this distributed generator will always operate in amplitude. And this converter will regulate the DC response. Okay, so C is correct. B is not correct because it can also discharge if required. But typically, generally it will charge. Overall, it will charge. So, which of the following type of load can cause instability issue under carrying loading condition? Yes, it is right. What's the answer? This is only the last. Constant power load can sometimes create but this is it's been a very easy question. Total hierarchical control
Centralized.
is this is based on poor voltage regulation in food control
Large
regulators.
gate quantities.
Or it is so this will result in if this is PMP this is large is this one clear? How is this type of quantities?
Yes, sir. Clear.
Which of the following entity is responsible to maintain the DC bus voltage in grid connected DC microgrid?
A is the answer. A.
A will be answered.
This is converter into DC bus to regulate the AC bus voltage. And this is an islanded hybrid AC-DC microgrid has excess renewable and fully charged storage, feeding uncontrollable loads both in AC and DC. A possible solution to maintain the system stability is, again I will read the question. It's an islanded hybrid microgrid with excess renewable generation. First it is islanded, then generation is excess. Storage is also fully charged and loads are being served. Which of the following will maintain the system stability?
B, sir,
B is
in
the
power
answer. B.
discharge mode.
B.
That we cannot charge this storage because it is already fully charged. Load shedding will what will happen if we shed? Yeah, the system stability.
It is power is already excess, sir, so no meaning of shedding the load.
Yes, correct. That is correct. There is no sense in doing that. Power is already excess. So load is already being high. So this is correct. Option B is correct. Any doubts? So I want to ask one thing. The way we are conducting this session, is it fine with some changes? Do you have any suggestions we can give? We'll try to change. Do you have any suggestions?
No, sir, the session is going good. So what is
Are these sessions beneficial?
beneficial, sir? Very much beneficial.
100% beneficial,
Only
sir.
one request. Please, that background noise is very high. So can you
So next time I will shift. I will change that. Please.
Especially today, sir.
I'm sorry for that. Next time, next time I will keep this.
Okay, thank you then. Thank you.
Thank you, sir.
Okay. Thank you. Meet next Tuesday.